works. Okay, so suppose x and y are related by, let's stick with the circle. Suppose x squared plus y squared equals 1. Okay, find the tangent line to the point 1/2 root 3 over 2. Notice that I've actually given you both the x and y coordinate. Usually if I want you to find a tangent line, I can just give you the x coordinate, right? Because you can always get the y coordinate from the original function. But there is no function in this case, right? So I have to give you both points. Okay. So let's look at this. So again, I want to kind of make this note here. Even though the circle is a very special case, in general, I mean, even for the circle, we're not going to solve for x or y or anything like that. Okay. So we make no attempt to solve for x or y. So please do not do that in any of your solutions. And like I said, for the most part, it's going to be impossible anyway, right? This is just a very special exception. Okay. But y equals f of x locally. Right? Again, keep this in mind, right? Even though I'm going to just draw the picture again very quickly to remind you, even if I have some weird looking graph, right, of some curve of just, I write down some equation, here's the graph of that equation, and I'm looking at one specific point. And I can still think of y as a function of x as long as I only concentrate on points near that given point. Now, we are going to even though I cannot find a formula for it, I'm still going to symbolically call this y equals f of x. So it's kind of like the following. So instead of having x squared plus y squared equals 1, it's as if I have x squared plus f of x squared equals 1. Okay. Again, this f of x, you should not think of it. It is not a function that describes the entire curve. It is a function that describes only a part of the curve, right? If we had a function that described the whole curve, that would actually be much easier. We didn't have to do this. Okay. Now, what is the slope of the tangent line in general? Maybe I should actually see what you guys say. This is covered on Monday's exam. What is the slope of this tangent line in general? The tangent line that we're trying to find? The derivative. Yeah, exactly. It's the derivative. The derivative gives you the slope of the tangent line. So the slope of the tangent line is dy dx or f prime of x. Now, how are we going to extract f prime of x here? We are not going to solve for f of x and then differentiate. We are going to use this equation directly. And so we can find f prime of x by simply differentiating everything in sight and then solving for f prime of x. Let me call this equation 1 so that we have... Let's get rid of that. Let me just move everything down a second. So let's call this equation 1 so I can refer to it. So we can find f prime of x from equation 1 by simply differentiating everything and solving for f prime of x. And we're actually going to notice that even though I can't solve for f of x, I will always be able to solve for f prime of x. Okay. Again, the reason we can actually do this is because if you start with an equation that is true for all x and y, and you differentiate it, you get another equation that is true for all x and y. But you can only do this if the equation is true for all x and y. You could not do this just for any old equation. Okay, so how do we differentiate 1? So when I differentiate equation 1, I will get equation 2. Now on the right side, I'm going to get 0, right? Because the derivative of a constant is 0. Mohammed, I'll give you the easy one. What's the derivative of the first term, x squared?
It's 2x.
2x. Good, you got the easy one. Now who's going to get the derivative? What is the derivative of f of x squared? Uh-oh. Justin, you're typing. Why don't you just tell us?
2y dy dx.
2y dy dx. So I'm going to use a different notation just because we're writing it right now in terms of functional notation. So 2f of x, f prime of x. What rule did you use there, Justin?
Is it implicit differentiation? I don't know.
This is implicit differentiation, but what derivative rule did you use? Did you use product rule, quotient rule, chain rule, something else?
Power.
Okay, you use power rule to differentiate the f of x squared. And what other rule did Justin use? Who wants to tell us?
It's chain rule.
It was chain rule, right? Exactly. Why was it chain rule? Let's make sure we all understand that. Let's go off to the side and do some scratch work here. All right. So the term I was trying to differentiate, let's call big f of x. So that was, actually, let's not call it. Let's just call it g. So g of x, that was f of x, and then that whole function gets squared. So is it more obvious now to everyone that we should use power rule and chain rule? So let's see. So what is the outside function? If we're going to say we use chain rule, we have to decide what is the outside function, what is the inside function. Who wants to tell us that? Nashika.
I think the inside function is f of x, and then the outside is x squared.
Very good. Good. And then when I find chain rule, remember how chain rule works, right? First, I differentiate the outside function, right? That's 2x, but I don't evaluate it at x. I evaluate it at whatever was already inside. So instead of an x, it's actually 2 f of x. And then I multiply by the derivative of the inside function, so times f prime of x. And so that is now what I've written in the actual problem. So, yeah, so we are using chain rule here. So implicit differentiation really is just chain rule. It really is, you know, it's what it comes down to. Okay, I will say, so what Justin said is how we actually typically write this equation. Instead of using this functional notation, because it really isn't, because even though the f of x refers to some local function, usually we'll just write it like this in terms of x and y directly. So 2x plus 2y dy dx. So f of x, y is f of x, and f prime of x is dy dx, right? So we usually use that notation instead. Okay, now remember what was our goal? To find a certain tangent line. So now we're going to algebraically solve for dy dx, and it will always be possible. Because you should actually think about how can dy dx actually appear in these equations. Dy dx is only ever going to pop out from quotient rule, product rule, or chain rule. And if you actually look at all three cases, that means you will always only ever get dy dx just multiplying something. You won't get dy dx squared. You won't get 1 over dy dx. You'll always just have dy dx just by itself, right? Maybe with some other stuff on multiplying it, but it's basically a linear equation. So now solve algebraically for dy dx. And we get what? We get that dy dx equals negative x over y. Now, I will say that for implicit differentiation, your derivative is allowed to depend on both x and y. I mean, that's going to be very natural, right? Your derivative will not just depend on x. It'll depend on both x and y. So for implicit functions, okay for dy dx to depend on x and y. Okay, now let's finish our tangent line. So the slope of the tangent line okay, so what was our point? The point that we were given was 1/2 root 3 over 2. Again, like I said, you'll usually be given both the x and y coordinates because giving 1 is usually not enough to get the other coordinate. Otherwise, you would have had a function. What is the slope? Well, what do? How do I get the slope? I take my point and I, again, substitute it into my derivative. I will just be substituting two numbers, right? The x coordinate and the y coordinate. So my slope here is negative 1/2 over root 3 over 2. So my slope is negative 1 over root 3. And my equation then, putting this all together, is y equals root 3 over 2 minus 1 over root 3 times x minus 1/2. And we're all done. Cool. Questions about that? So that was our introductory example to implicit differentiation. Questions, thoughts?
I have a question.
Yes, Hirsch?
So for I know you have to use chain rule for the y squared.
Sure.
So and then it turns out you have the derivative as 2y. So what happened to the chain rule? Or that is the chain rule essentially.
I didn't. Nothing happened. F of x is being replaced with y, and f prime of x is the same thing as dy dx.
Okay.
So this was just a notational change. It has nothing to do with calculus. But we don't really like to use the functional notation because we don't really want to emphasize that these are functions because they're not really functions. We're talking about locally defined functions, not a function for the whole entire curve.
Okay.